wrong thing. Here we go. All right, so we will only be checking at a single point today. So if you think about a graph, a function is continuous if you can trace it without picking up your pencil, right? So certainly something like a jump in the graph is going to make that non-continuous. A vertical asymptote in the graph makes the graph not continuous. What about a hole? If you have a hole in the graph, it is non-continuous. The limit exists, but it's not continuous for that. So for something to be continuous, it needs to be like a solid line, right? We don't have any holes, we don't have any jumps, we don't have any vertical asymptotes. So to prove that, there are three things that you must prove. A function f is continuous at a point x equals c, provided that f of c exists, limit as x approaches c of f of x exists, and the limit equals the value of f of c. So those three things broken down, you must show that f of c exists. You must show that the limit as x approaches c of f of x exists. And you must show that that limit as x approaches c of f of x is also equal to f of c. If any three of these fail, if you get no, it's not true, for any of these three, then that means that the function is not continuous. So as soon as you get that one of these fails, you can say function is not continuous at this point. So if you found that f of c does not exist, there's a vertical asymptote there, it does not exist, you would immediately say, well, no, this is not continuous at that point for those. So let's look at a couple things here. This is a little bit of a review going into proving continuity. So for some of these, I'm going to have to do one-sided limits for these. I'm going to have to think about the limit from the left and the limit from the right, because when I'm proving that that limit exists, I need to show that from the left and the right I'm going to the same point. So a note here is, what if I have an equation and I'm trying to do a one-sided limit, right? If you have a limit that exists, if the limit as x approaches c of f of x equals some number L. So if my limit from both sides exists, that means the limit from the left and the limit from the right are the same, right? So if you are asked to do a one-sided limit from an equation, you want to just treat it like it's a double-sided limit. Because if the double-sided limit exists, then the one-sided limit also exists, right? So if I saw an equation like this, what strategy would I probably use for this one? Factoring and canceling. I should check direct substitution first, but I'm seeing that -3 plus 3 on the bottom. Up here, that's going to be, let's see, 9 minus 15 plus 6. That's going to be 0 on the top as well. So direct substitution fails. So I am going to factor and cancel here. So I'm going to have the limit as x approaches -3 from the left of x plus 2, x plus 3, all over x plus 3. I can cancel my x plus 3's. Then I have a discontinuity. There is a hole. Right now, it's just asking me for the limit. So it's not asking me for continuity yet. So it is okay if I go ahead and continue here. So I would just plug in -3 now. -3 plus 2 equals -1. So we might need this a little bit later, so if you're asked to find a one-sided limit from an equation, just treat it like it's a double-sided limit because the left or the right has to be the same for that. Okay, that's just a little piece that we might need moving forward. Now, one-sided limits with piecewise functions. We did this a little bit yesterday because I used the limit notation when we were checking for continuity, right? So, if I am asked to find the limit as x approaches -2 from the right of f of x, and this is my function for f of x, which equation should I use here? The top equation or the bottom equation? It's going to be that bottom equation. And like I said, the book might throw something crazy at you like number 57 from last night, but in general, it's going to be left on top, right on bottom. So if I'm doing the limit as x approaches -2 from the right of f of x, for this equation, that would be the limit as x approaches -2 from the right of 3 over x, what's happening here, x plus 1, and this kind of looks like a discontinuity sort of problem, but x is approaching -2. So what do I do to solve this? Just plug it in. It's a direct substitution problem. So 3 over -2 plus 1 is going to give us 3 over -1, which is -3 for that. Now, what's happening here is, like, if you think of what that graph would look like, it's where your limits or your domains are changing for this. So at -2 over here, it's like that's the place where these two graphs switch, right? So for x is less than or equal to -2, I've got the square root function that looks like something like this right here. Over here, for the 3 over x plus 1, I've got a rational equation. You know, it looks something crazy like that. But that at -2 is the place that they switch. So you're looking at your domains here. It pretty much always, like, for these, they're almost always going to ask you about -2, the place where you're switching graphs. And unless they have tried to trick you up, and I will not do that, but I can't promise what Mr. Larson that wrote our book will do to you. The left is going to be on the top, the right is going to be on the bottom for that. So in this case, since you're approaching from the right, it's going to be this equation right here that you're dealing with. For limits, it does not matter whether it's the or equal to sign at all. Now, if I asked you to find f of -2, you would use the top equation because of the or equal to sign. But limits, it does not matter whether it's open or closed circle. It's what you're getting close to. So from the right, you would be getting close to the end of this function. Does that help? Okay, now what we're going to run into even more is part of what we're going to have to do to prove a limit exists, if they give us a piecewise function, is we're going to have to prove the limit from both sides exists for a piecewise function. So in this case, I can't just plug in 3 because I've got a piecewise function, right? In this case, I have got to do the limit from the left and the limit from the right to show that those are the same. So now, if this is a multiple choice question, you could plug in sort of like some of you did last night. Some of you last night had very little work on your paper. And I told you that was okay last night, because if I plug in 3 right here, I'm going to say I'm going to get 6 plus 5, that's 11. And if I plug in 3 right here, I get 14 minus 3, which is 11. So do I have a limit here? Is it continuous? Yes. But whenever we're asked to prove continuity, we have to write that out with limit notation to show mathematically that it has to be the case. We can't just say because I said so on these. It would be funny if somebody on the AP exam did just say because I said so, but I mean, kind of. Not if any of y'all did it, but if I was grading and saw it, I would laugh. And then I would still give them 0 points, but I would laugh. They also show up on multiple choice, and just the answer being 11 is enough for that. So for this, to do it properly, you need to do the limit as x approaches 3 from the left of f of x. And I like to write this step right here where I show very clearly that I'm choosing 2x plus 5. If you, I don't know why it's doing that. If you skip that step and go straight to 2 times 3 plus 5, you're probably okay there. And then you get 11 for that. And then you also have to do the limit as x approaches 3 from the right of f of x. And again, I like to show this step. I'm going to tell you from my experience grading, it sometimes can get you some points that you would have lost if you accidentally do something wrong. So like in this step, if you said 14 minus 11 equals 8 or something like that, you could still get the credit because you can see like they were choosing the right point. Maybe not the full credit, but you would get a point for that. So that is also 11. When you have a limit from the left and a limit from the right that are the same, this question is not asking you about the limit from the left and the limit from the right. It's asking you about the limit from both sides. So you would want to finish with a conclusion here. I like to put 3 dots that says, therefore, the limit as x approaches 3 of f of x equals 11. Like that. So if you're trying to prove a limit exists for a piecewise function, this is what you would do for this. Yeah, those you can, yeah. But those 3 dots mean therefore. So, and that's a mathematical symbol, so they'll take that on the AP exam. So it's not just like something I made up because I thought it was cute. It is used in actual mathematics. So, all right. So let's look at what you would do for proving that a function is continuous at x equals 2. So to go back, I'm going to just put over here, I'm gonna summarize the things that we've got to do here. We first have to show that f of 2 exists. Now you don't necessarily need to write this down every time, but because I'm trying to teach you the process, I'm going to write this down so we know what we're doing. You also need to show that the limit as x approaches 2 of f of x exists. And then we have to show that the limit as x approaches 2 of f of x equals f of 2. So we have to show that we have to show what we got for 1 and what we got for 2 are equal to each other. Those are our 3 steps right here. They do not necessarily have to be done in that order. 1 and 2 are interchangeable. If you want to do the limit first and then do f of 2, you can. I like to do f of 2 first because it's easy to forget it. Because when you do, like on this one, we're going to have to do limits from left and the right and make conclusions and stuff, and it's really easy to forget to do f of 2. So I like to do it first so you don't forget to do it for that. So the first thing that you want to do here is just find f of 2. And which function should we use to find f of 2, the top or the bottom? We're using the top because of the or equal to sign. So right now we care about the or equal to sign, and we are going to say 3 times 2 minus 4, and that is going to give us 6 minus 4, which is 2. And getting a number for that proves that it exists. So We have shown that f of 2 exists. For the second thing that we have to do here, we need to show that the limit as x approaches 2 exists. What we're dealing with here is, like at 2, that's where our piecewise function breaks apart, right? So we need to see if those two pieces connect up, or if we've got a jump or something there for that problem. So again, you can do it in your head to kind of see. 3 times 2 minus 4, we already did that, that's 2. 2 times 2 squared, that's going to be 8 minus 6, that's going to give us 2. This should exist, right? But you have to show it out whenever you're asked to do this on a free response question. So you're going to say the limit as x approaches 2 from the left of f of x. Piecewise functions, you pretty much have to do left and right limits for this. From the left, that means I'm using that top function. So I'm going to do the limit as x approaches 2 from the left of 3x minus 4. And that is a direct substitution. Most of these are, they usually don't give you super difficult ones here. They might occasionally, but not usually. So that gives you 6 minus 4, which is 2, right there. That is our limit from the left. We also must do our limit from the right. Which is limit as x approaches 2 from the right of the bottom function to x squared minus 6. So 2 times 2 squared minus 6. 2 squared is 4. 4 times 2 is 8. So 8 minus 6 also gives us 2 there. Show as much or as little work after you plug it in as you want. You can do it all in your head. They are going to assume that at this level of mathematics that you can complete that in your head. If you can't, or if you just feel better if you write it out, go ahead. You can show every step. It's fine. So we have found the limit from left and right are the same. So we can make the conclusion now that the limit as x approaches 2 of f of x does in fact equal 2. Okay, so we have proven that f of 2 exists. We have proven that the limit at as x approaches 2 of f of x exists. Did we get the same number for both of those things? We did. So we can, like, when we have this already written, we just need to, like, make a statement that the limit as x approaches 2 of f of x equals f of 2. And we have proven the three things that we need to prove for continuity. And we can now make the conclusion, therefore, f is continuous at x equals 2. Make sure you put at x equals 2. We have not proven this is continuous everywhere. We've just proved it at this single point. Nah, it'll be all together. It'll just say prove that this is continuous. So this would be like on that free response assignment that I gave you, it would be like one of the parts. Yeah. So you would have to do all of this for one part. Yeah. Usually.
Would you write 1, 2, 3?
It's okay if you do. If that helps you keep organized, you definitely don't have to. I like to keep organized when I'm teaching it to you guys so that you know what to look for. It'd be fine if you did, just to show like step 1, step 2, step 3 there, but you don't have to. But you do have to have all 3 parts. Okay, questions? It's a little bit annoying to have to do this for something that we did in our head at the very beginning. Like we knew that this worked from the very beginning, but we got to prove it mathematically. We got to, without a shadow of a doubt, show why this is the case for that. So, for this problem, I've got a piecewise function, and they are going to ask me about continuity at 2 different spots, at -3 and at 5. and it says justify your answer, or it might say show the work that leads to your answer. That means you got to show your work for that. And even if I forget to put it there, still show your work. Unless it's a multiple choice question, show your work, right? If it's multiple choice, I'm just grading it whether you got the answer right or not. So for this, if we go through, at -3, I would be using the top function and the bottom function. The first thing that I want to do for this is I want to do f of -3. And this is where I care about the or equal to sign. I use the top line. What do I get for f of -3? Just 2, because there's nowhere to plug it in, so I just get 2. That shows that this exists. That's our first step. Then, our second step, right here. We've got to show that the limit exists at that point. So we got to do limit from the left and limit from the right at -3. So the limit as x approaches -3 from the left of f of x is the limit as x approaches -3 from the left of just 2, which is just 2. And then I need to do the limit as x approaches -3 from the right of f of x, which means I should be using that middle equation. So 2x plus 4. And so that gives me 2 times -3 plus 4, which is, oh, what's that going to give me? -2. So my limit from the left and my limit from the right do not equal each other here. So I can say now limit as x approaches -3 of f of x does not exist. So f is not continuous at x equals -3. So as soon as something goes wrong, you can say that it's not the function is not continuous. I don't have to go on to say that the limit does not equal f of -3 because if the limit doesn't, any one thing that is not right tells you that you're not continuous there. Okay? Try 6 on your own. Try writing it out really neatly there. And I'm going to come around and check how you're doing on those. Let's see. Okay, so let's look at Kendall's first. So we can zoom in here enough to be able to see it. Okay, so definitely we got f of 5 equals 14. I think it's probably okay that Kendall did not show work there. Then Kendall showed the limit as x approaches 5 from the left and the limit as x approaches 5 from the right, and says 14 for both of these, which is correct. And then therefore the limit does exist. I think what she had, I'd love to go back and look at some like rubrics for questions like these. I think what Kendall has might be like a bare minimum possible answer. I think it might squeak by. What I would sort of like to see right here is like, I don't know for sure which equation you're using on that top one and bottom one, like that you're using the 2x plus 4 for this one and that you're using this here for that one. So I personally, as your math teacher, would like to see you either show like 2 times 5 plus 4, so I know that you plugged it into that one, or write a step where you're doing the limit as 2x plus 4 and then say that it equals 14, so I know you've chosen that right equation. But it might make it. It might there. And then you're saying that the limit equals f of 5 and therefore f is continuous. So I think it would squeak by. I would probably prefer to see a little bit more work right here. There. Especially like if you mess up. If your work is there, you might have enough for some partial credit. Whereas if you get it right, it might squeak by. If you get it wrong, it'd be a 0 for that. So that's one of the things I'd like to see. A little bit more work. It's pretty good. We got the pieces that we need. Rowan's is even smaller right here. He's committed to the box right there. It's not as bad, but when I blow it up, it looks super fuzzy. So, but let's check and see what he's got here. F of 5 equals, showed the work for plugging in, got 14. That looks good. I like that. Limit from the left showed that he was using 2x plus 4. That's that step I'd kind of like to see. Also showed that he plugged it in and then got 14. I like that. From the right, showed that you're using this one, plugged it in. It gets a little messy here, but he is trying to squeeze it in. Gets a 14 here. So he says that the limit is 14. And then concludes that it is continuous. I think this one will get by for that. He's kind of skipped a step, right? He's kind of skipped that third step. Because he's not showing that what he got for f of 5 equals that limit. I think as long as he has showed his work very clearly, where he's got f of 5 up here equals 14. And I can very clearly see he got 14 there. And I can very clearly see he got 14 for his limit. That it can be understood that those are equal. If your notation is bad, if you don't use an f of 5 right here, then I don't think that's going to squeak by. Listing it as a separate step is like your best foolproof way, so that if you did have a little bit of mess up somewhere else, that it would probably, be the best to look at there. So let me get these back, and let me look and see. I need to show you how to set up 7, and then I will let you go through that one here. I'm not going to know how to do your assignment. If you skip the last 2, it's not going to hurt that much. But 7 we at least need to set up, because 7's a little bit different type of problem. So we're going to squeeze this in here for 7. All right, what's different about this one? X is not equal to. That means we use this function everywhere except for at 3, right? So whenever I'm doing this problem, it's asking me for what value would make B would make this continuous. My f of 3 is B, right? And then I'm not doing a one-sided limit for these, because while this is a piecewise function, there's not a left and a right side to it. There is this function everywhere, and then a B that plugs in the hole right here. So what I'm going to do is I'm going to just do a double-sided limit on that one. So that's like my step 1 here. This is my step 2. We're doing limit as x approaches 3 of x minus 3 over x squared minus 2x minus 3. And how do I do a limit of a rational function like that? I'm going to factor, so I'm going to have x minus 3 on top. I will have x minus 3, x plus 1 on the bottom. These will cancel. That means I'm doing the limit as x approaches 3 of 1 over x plus 1, which gives me 1 over 3 plus 1, so 1/4. So what's happening here is I've got a whole, right? And that y value of the whole is 1/4 whenever I find this limit. So like on my graph, whatever it looks like, right here, there's the whole. The x coordinate is 3. The y coordinate is 1/4 for that whole right there. So if I want to make this continuous, I need to fill in that hole with a dot, right? So in this one, you're not proving continuity. You're finding the b value that would make this continuous. So what you have to have is that this limit has to equal f of 3, right? The limit that we got was 1/4. It has to equal f of 3, which was just your b value, right? So in this case, b is going to equal 1/4. This is almost just a way of asking you a different limit problem, okay? I think we should be okay that we did not get to the last 2 examples here. You have an assignment on AP Classroom. It has 6 questions. They are multiple choice, so you don't have to show work necessarily for them, but you have to reason through them using these 3 steps, like this, okay? So the AP Classroom is your assignment over the weekend.